This is a great problem that came in this year in electrical engineering paper, and this is a problem that concerns the circuit containing multiple diodes. So in this case, there are two diodes, and the problem is stated as follows. In the given circuit, the diodes are ideal. The current I through the diode D1 in milliampere is dash, and the answer should be rounded up to 2 decimal places. So this is the diode based circuit, and here is diode D2 and this is the diode D1, and our objective is to find out the current that flows through the diode D1, and we can find that all the resistances are 1 kilo ohm, and the voltage sources on the left hand side, this is 10 volt, and on the right hand side this one is 3 volt. So the way to proceed with this sort of problem is to look at the fact that this depth of these two resistances along with the voltage source, this forms a voltage divider, and then we can of course treat the right hand portion, that means the portion following this on the right hand side, we can treat it as a load network and then go ahead and find out the Thevenin equivalent model for this particular circuit. And this is easy to evaluate because this is just a voltage divider. So the Thevenin equivalent voltage VTH is equal to 1 kilo ohm by 1 plus 1 kilo ohm multiplied by the voltage at the top, which is 10 volts, and therefore VTH is equal to 5 volts. And finding out R Thevenin is also easy because the load will be open circuited, and from this open circuited terminal we have to look into the network and suppress the voltage sources. So this becomes ground, and we have 1 kilo ohm in parallel to 1 kilo ohm, and that becomes R Thevenin. So R Thevenin turns out to be 1 kilo ohm parallel 1 kilo ohm equal to 0.5 kilo ohm, and then we can go ahead and replace this part of the network with the Thevenin equivalent model. So this is the Thevenin equivalent model, and so we have this 5 volt Thevenin voltage source, the Thevenin equivalent resistance of 0.5 kilo ohm followed by diode D2 and resistance 1 kilo ohm, and then this is a branch comprising the diode, and then the other one has a resistance that goes to ground. So in the next part, what we do is whenever you have multiple diodes, the idea is to start working by assuming that all the diodes are on, unless of course you are in a situation where you can happily say that okay, this diode will be on and this diode will be off based on the voltages provided. But unless we have a clear picture, we are unable to identify whether the diode D1 should be on or D2 should be on, or maybe D1 should be off and D2 should be on, like so. So it's safer to assume that both the diodes are conducting and then start your evaluation. Now, if you find that one of the current that flows through the diode has an opposite direction, that means instead of flowing from, let's say, from anode to cathode, it turns out that it flows from cathode to anode, then you have to again re-evaluate the circuit by open circuiting that particular diode and then work out the problem once again. So by the starting assumption that both the diodes should be on, we have replaced diode D2 by its ideal model, which is a short circuit. Similarly, we have also replaced diode D1 by its ideal model, which is a short circuit. And this is the particular structure. So our objective is to find out this current I1, and if I assume that the current that flows into this node from the left hand side is I1, and then this top current is I, and this current is I2, then obviously I is equal to I1 in negation plus I2, or in other words, I is equal to outgoing current minus the other incoming current. And we can find out the value for I1. So this is the current I1, the current that is flowing through this branch, and we know that the voltage at this node is equal to 3 volt, voltage at the other node is equal to 5 volt. So 5 minus of 3 divided by 0.5 kilo ohm plus 1 kilo ohm, that is the value for I1. So this is the value for I1. And then for I2, we note that this node is at 3 volts, whereas the other node is at 0 volt, and the resistance is 1 kilo ohm. So this is 3 minus of 0 divided by 1 kilo ohm. Simple use of Ohm's law. And from here, if we do this little algebra, it turns out that I is equal to 1.67 milliamperes. So you have to state the answer in 2 decimal places. And so we find that the value of I is equal to 1.67 milliamperes. Later on in this course, I will take up some problems where you will find that the voltage sources are such that it might turn out that one of the diodes will be off, and then we have to re-evaluate the circuit. But in this case, luckily enough, we had a very simple case and we could straight away, with our starting assumption, find out the solution.